Hello, hello.
Hello.
Can you hear or see me?
Yep.
I'm hearing echo right now. Oh,
Can you
okay.
hear me?
Yes, I,
Great.
yep. But I'm wondering why the virtual background is not working.
I see your Caltech pendant.
Yep. And a lot of other things, which
Yeah.
I'm kind of
It
embarrassed of. Uh, I I think the virtual background is like being processed or something.
mm, I didn't try to use
Yes.
one, so I'm fine without it.
But well, your office, nice. Are you in the office?
Yeah, I'm in the office.
Okay. Let's see if I can blur the background and make it look a little nicer.
Mhm.
In the meantime, you can try to share your screen.
Okay. Okay, you should be able to see it now.
Should I? Yes. Yes.
Unfortunately, I can't see anything.
You
I can
cannot.
only, I mean, I can see my own stuff, but I can't see you anymore, and I don't like even see the application. So it's fine. I don't really need to,
Hmm,
as long as I don't need to see my video image or you or anything like that, then we should be good.
okay. But on the audience side, we will see your screen, your video with your face, and
You can still
then
see my face?
because yeah, I'm the host, so I'm seeing myself. So
Yeah. Um, I'm wondering if I should change my screen over to the other side so that I can look directly. So just give me,
maybe, yeah.
actually, I will stop sharing. Actually,
I think if you're on two screens, I think you can use one for each task. I think.
yeah. So can you see the right thing now?
Yep.
Great. Hopefully you don't see the version with like the notes and stuff. You just see the regular presentation
Uh,
mode.
right. No, I don't see the notes and stuff.
Great. And I can change my pointer so I have a laser. Yeah, I don't see the clock, so I'm going to get my phone. There we go. So we still have 6 minutes. It looks like 5.
Yep. Yep. Do you see the um, the audience?
No, I don't see anything from the from the app.
Yeah.
The only
Yeah.
thing I have is like a button to stop sharing, but I don't see anything else.
Right. I don't know why they don't see, they don't show the audience to the presenter.
Yeah.
And I believe that the audience also don't see one another.
Hmm.
Hmm.
So is
So,
everyone in the audience online?
not, yes, they will be online, but
Okay.
not right now.
Okay.
Hopefully in a few minutes.
Sounds
Yep.
good.
I was about to say that there will be, I think, 40 or something people
Okay.
joining us today.
Great. And they're mostly students, right?
And professors.
Oh, really? Okay.
Yeah.
probably should have made it a bit more technically heavy, but are these professors
Yeah, not
from
necessarily.
all over material science, or are they specifically from electrochemistry backgrounds?
I think all over, also from chemistry, chemical
Okay,
engineering,
okay, good.
and maybe physics.
Okay.
So are you still on like during this time you're on sabbatical, right?
Yeah, I'm on
Then
sabbatical.
you still go to campus sometimes.
Yeah, a lot. But next semester I will not because I'm going to British Columbia, as you know. So yeah, I will be fully off campus starting in January.
Okay. Yeah, a friend of mine is taking sabbatical also,
Hmm.
starting from July, I think.
Oh, interesting. That's good. And will your friend take it 1 year or just one
1 year.
semester? 1 year. That's good. It's nice to have that time. I think if I had only taken one semester, I would have felt like it's way too short. I wouldn't
Yeah,
have gotten
especially you
anything
spend
done.
1 semester on campus already.
Yeah, yeah. But we worked on our house a lot, so it feels like I've been working really hard. But the reality is, I am finding some spare time to do other things. I mean, I'm using that time to restore our house. But
Uh, by the way, um, there are some audience in the room already, so
I
if
see.
you want to keep things private,
Got it. Thank you.
yep. It's it's the final exam week here.
Okay.
Uh, Actually, today is the first day. This morning, I was um, overlooking the examination process.
Yeah. Oh, great. So does that mean soon you will have a break?
Yes, it's like New Year, not much of the Christmas break.
Okay. So not right away, but maybe in 3 or 4 weeks you still have 3 or 4 weeks
Uh,
of the semester.
yep,
Okay.
yep. Well, the student will have like the times off after I think um, the middle of December, but professors never have long vacation anyway.
Hmm. Yeah, for sure. But we have an interesting job, so
Yep.
there are rewards.
All right, I'm gonna try to change my background again because I still see a lot of stuff. My colleague mentioned about a conference. I'm not sure if it's ECS in Toronto next year
Hmm. Not Montreal?
or Montreal, maybe.
I think ECS is in Montreal next year. Yeah, I was invited, but
Okay.
I decided to abstain because I just want to protect my time a little bit. So I decided not to go
Ah,
to that conference. But yeah, it looks like a really nice conference. I would love to go to Montreal. So it
hmm.
was it was a hard one to say no to, but
I'm
sometimes
considering
time
it though.
is too much. You're considering?
Yeah.
Yeah, you should go.
Yep.
It's a beautiful city, and as you know, they speak French there. It's a very bilingual city, so like in all of Quebec, French is the first language, but in Montreal, it's more of a mix of English and French, just because of how international the city is. So it's a really neat place, very special place, very different from France, but also
Mhm.
very different from English speaking Canada.
I heard that some people from Quebec don't even speak English. Is it true?
Yeah, yeah, that's true. Yeah, there's large parts of Quebec where people don't speak much or any English, and they have a very proud tradition that especially centers on language. So um, this is a really important part of Canadian culture as a whole. And it's not only in Quebec. There's also parts of other provinces where people speak mainly French, but obviously Quebec is the biggest French francophone, province that we have, and so it's the center of the French Canadian culture in Canada. It's a
I,
beautiful place.
I should really considering going there.
Yes, yeah, it's a very nice city.
All right. So now there are like 20 people in the room. So should we wait a little bit or wanna start?
Um, we can wait or get started, whatever. It's up to you. As you could
Uh,
imagine, I don't really have very many other things going on right now here, so I'm available.
but it's like is it midnight there?
It's 11 p.m.,
Okay.
but it will be midnight. It'll be closer to midnight when we finish this. So I don't have another meeting to go to after this.
Thank you for doing this talk
No problem.
at this time, which is very late over there. So I really appreciate it, and I hope that the audience are also appreciate your time.
I'm very grateful for this opportunity. So thank you for having me.
All right. I think we can start now. All right. So whenever you are ready,
Okay.
I think I click everything, and the audience should be able to see things already. All
Okay.
right. So the stage is yours.
Okay. Well, thank you very much, chat. Um, Thanks everyone for being here and for giving me this opportunity to talk to you today. So I'm gonna give you a pretty introductory talk. I didn't quite know what the level of this audience would be, so I decided to make it as kind of introductory as I possibly could on the topic of silicon anodes for lithium-ion batteries. And this is an area of pretty big importance. I'm sure you've all at least heard a little bit about this because there's quite a buzz that silicon will replace at least a small fraction of the sort of state of the art anode in lithium ion batteries, if not the entire anode in your lithium ion batteries that are either in your laptop computers or your phone, and maybe also your electric vehicle. So it's a big area of research right now, and there's a lot of fundamental research going on. There's also all the way to the very applied end of the spectrum, and our group is somewhere right in the middle of that. And I think it's useful to kind of see this topic kind of from in a very simplistic treatment, because I hope it'll also sort of drive home some very basic concepts about what are the materials of highest interest for next generation batteries. Where do they come from? How do we all start reasoning through it from scratch, not just I'm not just here to tell you today, here's some very fancy material and here's how it works. It's more like, let's think about this in the most simplistic way possible. I will also admit that that's how I had to start doing this research because I was not an expert in silicon before getting into this. And so some of what you'll see in this talk is part of my own thought process as I got into this. So my name is Nick Stadie, and I'm in the Department of Chemistry and Biochemistry at Montana State University. This is a relatively small, kind of off the main map university in the United States, and maybe a place that you've never heard of before. So in case you've never heard of it, we are in the north central part of the U.S., just south of the Canadian border. Um, and we have a material science program here. I also have a PhD in material science, so I'm very fond of that program. And my group contains chemists and material scientists combined. So thank you very much for being here, and I'll get started. So the overview of today's talk is going to be, as I mentioned, about silicon, but we're going to start with just some basics of lithium-ion batteries, then some basics around silicon, um, and then kind of showing you some data and talking through how we did some problem solving in terms of early problems with our silicon anodes, which had to do with electrolyte, and then some of the solutions that we came up with to really start to stabilize silicon. You'll see that silicon has major issues with stability compared to other anode materials. And so there's two main strategies I'm going to talk to you about today. One of them is particle size engineering, and the other is doping. And then I'll show you a little bit about future work and kind of summarize where silicon is today. Okay, so here is my own version of a schematic of a lithium-ion battery. I'm showing you this schematic in discharge mode, which is the downhill, thermodynamically downhill mode of operation of a battery. Okay, a secondary battery or rechargeable battery can be used in either direction. That's the whole point of it. And so you have both an uphill and a downhill direction of operation. And here I'm, all the arrows and the flow of both electrons and ions corresponds to the thermodynamically downhill direction. So in this image, as I'm sure you've seen many such schematics before, there are two electrodes. Okay, these are these striped materials here. This is kind of the striping effect implies that they're both layered materials, so their crystal structures are layered. But the important thing about them is that they both store as much lithium as possible and at under very different thermodynamic states. So the material on the cathode side, we see electrons and ions flowing into this material in the downhill direction of operation. So that implies that the lithium should find a very thermodynamically favorable home in the cathode material. So that's what defines a good cathode material for lithium-ion batteries. On the other side, we have an anode, and that material sort of should have a relatively unfavorable thermodynamic site for lithium storage, but equally dense and high capacity, so that you have an efficient or effective overall cell. In the middle, you have an electrolyte, and basically, in all rechargeable batteries today, we use some kind of a liquid electrolyte. They consist typically of some solvent. Here we see some carbonate-based solvent. That's what these gray and red molecules are. And then we see ions. So we see the lithium ions in yellow, and then a counter ion, typically something like hexafluorophosphate, which is there to balance the charge in the electrolyte. So those are your main components of an electrolyte, or sorry, of a lithium-ion battery. And today we're going to focus a lot on on the anode side here, and talk about what's being used now, which is, as you might be aware, is graphite, and what could replace that in the form of silicon. Okay, so when we talk about thermodynamics and compared to in battery speak, we have the material of actually relatively high energy or unfavorable thermodynamics has a relatively low electrochemical potential. So that's just the convention of how those two things correspond to each other. And so what does a lithiation state look like in graphite, for example? So if we zoom in and look at the atomistic crystal structure of graphite, graphite is, of course, a pure carbon material. It contains six-membered rings, just like benzene, but instead of any hydrogen, all the carbons are bonded together in this sp2 hybridization state all the way through this entire layer, and it's a perfectly flat sheet sp2 hybridized carbons. And then those layers are stacked on top of each other in A-B stacking sequence. So layer A is just a little bit mispositioned from layer B, and then it goes back to layer A, layer B, and layer A, and so forth. So that's graphite, a well-known crystal structure. And when we lithiate it to the maximum composition of lithium, we get a stoichiometry of LiC6, and it basically looks like this. The lithium slips in between the graphitic layers. And I am showing you here a realistic depiction of, to scale, how much those layers need to kind of widen in order to accept lithium in between them. It's not very much, and you can barely detect it by eye. When lithium goes into graphite, we can squeeze in lithium, like I said, up to this LiC6 composition. That corresponds to around 4 angstroms distance between each lithium ion. That's an extremely narrow or short distance between lithiums. For comparison here, solid lithium is only separated by around 3.1 angstroms between each lithium atom. So this is a relatively high density state of lithium inside of graphite. And by the way, this 4.3 angstrom distance is in between the planes. If you look at the distance from lithium to lithium through the planes, it's only 3.7 angstroms. So this is a relatively dense state of lithium. Carbon itself is very lightweight and highly abundant. So this material represents a pretty effective solution for storing lithium. It's light, it's dense, and its electrochemical potential is extremely low. In fact, only 1/10 of a volt higher than lithium metal. And you can't go lower than lithium metal, because if you do, you'll just plate lithium metal onto whatever your electrode is made out of. So things in the world of lithium-ion anodes are quite good. They're really good. But as with anything, there are some, there are constantly demands for better performance. One, as we all have the same frustration, we'd love to have a phone that weighs the same amount but stores more lithium, or has a higher capacity on each of the electrodes. That way, your phone would simply last longer, not weigh anymore. Okay, there's lots of different performance metrics one could hope for. The one that my research gets sort of funded by the most, the motivation for us, is because my research is funded largely by U.S. military. Um, the U.S. has recently become very concerned about not having a sort of domestic supply chain for graphite, and that came to a head in 2023, in October of 2023. So about a year ago, China China, who's the world's largest producer of graphite, um, employed lots of export controls on graphite basically overnight. Um, and this caused a lot of distress on the US side for, even incentivizing it even stronger to have some kind of a local or national supply chain for this anode, which, the US just knows they don't have very much graphite in the US, and so they have to either make it synthetically or look for other anode materials. And this is obviously spurring a lot of research here to replace it. So here is a comparison between lithium and graphite, um, to point out that you can actually use just lithium metal as an anode material in a lithium-ion battery is maybe somewhat obvious, but in case you haven't heard, this material suffers from a lot of issues. One of the most famous or notorious of which is that when you plate and strip lithium over and over and over again inside of an electrochemical cell, especially in a liquid electrolyte, but even when you use a solid electrolyte, you grow dendrites that can basically, so instead of just plating and stripping neatly in nice sheets on your electrode, lithium stacks up and grows in kind of tree-like formations that eventually have pretty surprisingly high mechanical durability, and can poke through separators and even cell cases in some cases, depending on what it's made out of. And you get short circuiting of a cell relatively often when you're using a lithium metal anode. And so this material has been outlawed, or kind of pushed to the side for a long time. It's coming back now because of solid electrolytes, but still not being proven as an anode. So what other kinds of materials could we imagine to use to store lithium? I mean, we like the light weight of graphite. So what are some other allotropes of carbon? Well, the most famous other bulk allotrope is diamond. Diamond is an insulator. Okay, it's got lots of other issues. It doesn't store lithium. Okay, clearly not a good material. But interestingly, despite diamond's failings, okay, if you go just one element lower in the periodic table and go to silicon, okay, silicon has the same crystal structure as diamond, but all of a sudden it's a semiconductor that you can actually dope to make, a reasonable conductor. Also, when you put lithium into it, not only do you get a relatively large amount of lithium, these are the metrics here. So we see this is the lithiation capacity in units of milliamp hours per gram in this line here. Far, far more lithium goes into silicon than into graphite on a per gram scale, even though silicon itself weighs more than carbon. Also, you get a really a massive density of silicon on a per volume scale. So this number 9780 is in units of milliamp hours per milliliter. It's way more lithium than you can squeeze into lithium when it's all by itself. So bulk metallic lithium has a lower amount of lithium per volume than silicon. Okay, this is actually a pretty common property of materials that store very light elements like hydrogen and lithium. And I come from a hydrogen storage background, and it's well known that metal hydrides they can also densify hydrogen to higher densities than you can get in just pure solid hydrogen. And so that's the same effect is being shown here. You can take lithium and you can put it into silicon and get much higher density lithium than you could in just bulk metallic lithium. So the stoichiometry, there's actually two potential stoichiometries of target for lithium and silicon. One of them is Li22Si5. This has been made metallurgically, um, typically requires high temperatures and high pressures, or lithium 15Si4. This is the sort of realistic final stoichiometry for lithium and silicon. This is the one that you can achieve at room temperature in an electrochemical cell. And so we're going to focus on this stoichiometry in this talk. Still, these numbers are very, very high and make silicon a pretty attractive potential replacement for graphite. Okay, another point here is that it has a low electrochemical potential, which is what you want for an anode. It's not quite as low as graphite, certainly not as low as lithium, but it's still very low and uh, makes it a very considerable material. Okay, so what happens when I take silicon and I put it in place of graphite on the anode side of a typical lithium ion battery? I'm not going to change anything else about the cell. Well, okay, I'm going to skip this slide actually because this is a little bit too much information for this. We can come back to that later in a minute. Okay, so here is just some raw data. These were collected pretty early on in our investigations of lithiation of silicon. We basically just bought silicon off the shelf in the form of 100 nanometer nanoparticles here from Sigma Aldrich, and we made our electrodes in the same way as we'd make a graphite-based electrode. What you're seeing on this plot is the discharge capacity of that electrode in a half cell configuration as a function of cycle. Okay, that's in red. So, and in blue, we're seeing the Coulombic efficiency, which is really just saying, what's the discharge capacity divided by the charge capacity. This fraction should be equal to 1 if things are kind of behaving well in the cell. But let's look at the discharge potential or the discharge capacity. It's clear that you can get a very, very high numbers of, say, 2,800 milliamp hours per gram. This is about 10 times the amount that you would get in a graphite cell on a per gram basis. But that number does not stay remotely stable. It falls relatively quickly with cycling. So by the time you get down to 200 cycles, you're at less than half of what you started with. Now these data that I'm showing you on the left side are actually some of the best data we ever collected in our early studies of silicon. We scanned a lot of different potential precursor materials across different sizes of nanoparticles, different suppliers. Okay, these are some of the best data that we collected. On the right is a much more typical set of data. So this is a different supplier. These are 1 micron sized microparticles, and lo and behold, okay, we get a decently high capacity on cycle 1, but then it rapidly declines and you get almost no capacity by the time you're at cycle 50. So just from the perspective of an experimentalist just cycling a cell, this silicon is behaving very, very differently from graphite. It has a lot of issues with stability, and it does show high capacities early on, but that rapidly gives away to much lower capacities, and in some cases, almost zero by the time you get out to 50 cycles. Okay, to compare with graphite, this is basically the benchmark set of data that are currently collected on graphite. This cell is the famous Jeff Dahn um, 4 million-mile cell, and what it shows you is, and so this cell has been cycling in the lab of a very famous battery chemist by the name of Jeff Dahn up in Halifax, Canada, for years, and it's got now some 5,000 cycles, still above 95% of its original capacity, which again for graphite is 372 milliamp hours per gram at best. And so while that's a low number on the left plot, okay, that's an extraordinarily stable cycling, and we can see that these data on the left will definitely intercept 372 here well before even 500 cycles are passed. So what's the cause of this problem? It's not just us not being able to make a good quality electrode. It really is something inherent to silicon in the way that it works. And the answer to this question is there is no such thing as a free lunch. So while on paper silicon looks like a fantastic anode to replace graphite with, it has a better gravimetric capacity. It has even a better volumetric capacity of lithium than even bulk metallic lithium. Okay, this leads to some really serious differences in chemistry. So what does it mean? Here is a picture of a collection of 100 atoms of silicon in its native diamond structure. Okay, and this is a two-scale uh, demonstration of what that same number of atoms of silicon looks like when you fully lithiate it to Li15Si4. This is again the maximum lithiation state that you can achieve in an electrochemical cell. This corresponds to a 300% expansion on a per volume level, and is absolutely massive in from a just from the general viewpoint of how energy storage materials work. So to give you some numbers on lithium distances here, I looked it up. There's these sites are somewhat more disordered and they're not as nicely symmetrical as they are in LIC6, but the closest distances are on the order of 2.7 to 2.8 angstroms, so smaller than, but just slightly below what it would be in metallic lithium. That is really a key difference between how silicon and graphite work. And so as a driving message today, I mean, silicon, yes, on paper looks great, but when you actually look at the mechanism of lithiation of silicon, you must be asking yourself, is that a sustainable lithiation reaction over and over and over again and back and forth in an electrochemical cell? You'll notice that I've not drawn any silicon bonds because these silicon bonds, every single one of them in the original silicon lattice is far too, each silicon distance is far too long to be considered as any kind of a bond. This is a completely different material. It's basically a sort of alloy at this point, and you break and make every single one of those silicon bonds every single time you charge and discharge this material. So that explains why you have this rapid loss of capacity with cycling as you expand, contract, expand, contract, expand, contract your silicon anode. You're going, those particles are occasionally being lost from electrical contact on your electrode, and they're basically just swimming away. If you lose a particle from electrical contact on your anode, you can no longer lithiate or delithiate it in the next cycle, and that's basically what's understood to be going on here, even in the best case scenario for silicon, happening rapidly in the case of these much larger particles. I'm on the side on the right. Okay, so when I show the same data as I just showed on the previous slide to higher cycle number, we actually saw another interesting effect that we were very confused by in early work on this material. And we had never seen this before with graphite, for example. And so we spent a lot of time wondering about it. And basically, what would happen is that you'd get a kind of linear trend in capacity fade, but then all of a sudden it would fall off a cliff, and then it would level out eventually, but you'd get a very dramatic loss of capacity at a certain cycle number, just around 200. And so we spent a little while wondering about this, but I am going to actually, I'm going to skip that slide. We had tips from our Army collaborators telling us that, well, this is because of our lithium chip. And so they were really focused on the fact that we were running these cells in half cell configuration. And we're pretty sure that this would also happen in the sort of, it would get fixed if we had placed the cell in the presence of a different counter electrode. And so we started investigating LFP, lithium iron phosphate, as a potential counter electrode to try to solve this problem, but it did not solve the problem. We still had lots of capacity fade, and things were even worse basically for LFP than they were for the chip. So when we went back and we had to look into the electrolyte chemistry. And on this slide, I'm showing you the same exact electrode, charged and discharged in the presence of an additive, an electrolyte additive called FEC, fluoroethylene carbonate. It was only present in 2% ratio in the original electrolyte here in red. When we increased that to 10%, for example, we managed to solve this problem completely. So electrolyte engineering has a very important role in any kind of lithium-ion battery research. And I guess the main takeaway message here is you've often got to just try a lot of different things. And whenever you're changing any of the chemistry in your cell, you should expect that there will be problems with whatever you were using before in terms of whether it's electrolyte composition, cathode compatibility, different things like this. And so even things as small as the compatibility with the metal that your coin cell or pouch cell is made out of. Um, this was just to say that we did eventually solve this kind of problem. We could cycle our cells now to much longer cycle number, although we did not solve the overall capacity fade issues associated with silicon. So the postdoc in my lab at the time had an interesting idea. He decided and showed us these data one day in group meeting where kind of on his own, he had just gone in and decided, I'm going to try to mix different precursors together. So we had, and this was actually motivated mainly by the practical issue that we actually ran out of that really good 100 nanometer silicon particle. We completely used up our stock of it. We tried to replace it, and whatever we bought from Sigma Aldrich the second, third, and fourth times was never as good as that first bottle. And so that was an issue that it was an interesting one to us. Even the same supplier, nominally the same material, did not have the same performance properties um, in different rounds of buying it. And so my postdoc decided, he wasn't going to wait around, and he was too impatient to figure that problem out. And so he decided to just start by mixing different, precursors in the lab that we already had. So in this case, he's mixing that one micron sized microparticle silicon, the one that really doesn't do well, together with this 50 nanometer precursor that we had sitting around in the lab. The 50 nanometer precursor was probably one of the smaller nanoparticles that we had of silicon. It wasn't a great material on its own, and it was pretty hard to handle. So we didn't really like working with it. It was very fluffy. But what he did was he made mixtures of it. So here we have a 0%, 10, 30, 50, 70, and 100% mixtures between a 50 nanometer and a 1 micron particle silicon. And you can see here what happens when you have no nano. So this is the 1 micron particle. Again, it pretty much dies before cycle 40. This is a pretty representative case for not having any nano particles at all. And as soon as Wei added just a little bit of the nanoparticle system, here we have the 10% mixture. So this is 10% nanoparticles, 90% micron particles. You got a massive improvement. When he added 30%, it went up to this blue line. 50% is purple, 70% is orange, and this green line represents the 100% nano system. So there's a real synergistic effect here that if you mix these two materials together, it doesn't just give you a linear combination of effects of the nano plus the micron, because then you would expect everything here to fall in between these two cases. Instead, there's actually a significant improvement to be had by mixing the two together. Um, so this was a remarkable discovery, and we decided to go forward with this full throttle because this was a really interesting way to improve our silicon anode performance. The the material that has the 30% composition of nano in the presence of 70% micron is shown in red here on the right and the left. On the left, we have this previously the best sample we had ever gotten our hands on. This silicon, or sorry, this 100 nanometer nanoparticle from Sigma Aldrich, unmixed. And you can see that while that material did better in early cycles, it always did worse in later cycles. And so we now had, you know, a much better material than we ever had as a pure silicon nanoparticle phase. This was the best one we ever made in our own lab. And when we talk to companies making pure silicon anodes, the only commercial operation that would actually send us electrodes was this company Paraclete, and their material that had around the same loading as our material was significantly performing worse. So we were really happy with these results, and we think particle mixing is probably an uh, underexplored area, especially in silicon, but maybe even in other aspects of battery electrochemistry. Now, that number of 30% nano, 70% micron, I couldn't help but wonder if it had anything to do with the kind of sphere packing ratio. So as many of you might know, the close packing, the highest close packing density that you can achieve is 74% volume per volume with spheres. Now, our particles are probably not exact spheres; they're probably not close packed. But I just thought that that was too much of a coincidence not to at least think about. And it gave me this kind of picture that when we were packing in 30% of the 50 nanometer particles with 70% micron sized particles, we were probably making some kind of nearly perfect amount of glue in between those interstitial voids of the 1 micron particles, and that may be the reason why the optimal combination is a 30-70 mixture. There's no evidence of that, but it's just purely a speculation. When Izzy, one of the grad students in our group, went and tried to just make other 30-70 mixtures with other random combinations of things, I mean, none of them worked as well as the original 50 nanometer 1 micron mixture that our postdoc was able to come up with. And so um, this is a pretty good evidence that something about a really small particle in the presence of a really large particle is kind of what you want in this case. Here we have electrochemical impedance spectroscopy. In case this is something you're not very well familiar with, I don't have time to go into the kind of the introductory details of how this works, but what I will show you are some data anyways, and those of you who kind of can follow along. So we have, this is a Nyquist plot, and we see some of the two semicircular features in our electrochemical impedance spectra of this very like nice mixture Si30. And they show pretty good stability over those first 40 cycles, which is what we like to see. Cycle 0 obviously being different because you have to set up a lot of solid electrolyte interphase in that first cycle. Okay, but this relative stability of the electrode over the first 40 cycles was very promising for us as compared to any other silicon that we'd ever looked at. Here we have in cycle 0, and I'll show you a later cycle, what's going on in different mixture combinations. So when you have a pure micron-sized particle, you have versus a 30% mixture versus a 100% nano system in blue, you have pretty similar kind of effects going on at the electrolyte electrode interface, which is what this first semicircle is representing, but very different behavior within the bulk of the electrode. And so the silicon micron sized particle is having a very, very sort of resistive effect for lithiation in cycle 0 as compared to the nanophase. So this might make, logical sense that if you have a smaller particle, you have also maybe more defects and lots of reasons why lithium might be able to have less resistance kind of in moving into the nanophase material versus the micron. The Si30 shoots just in between. So here we have a case where this really is now maybe something just in between these two phases, right in cycle 0. Now, interestingly, as you continue to cycle those electrodes, the nano phase, which used to be the kind of least resistive one, turns out to be a lot more like the Si0. It's starting to act a lot more resistive, sort of similar to micron-sized particles. Okay, even though it's made purely out of nano size and very small nano sized particles of silicon. Meanwhile, the Si30 shows the sort of the least um, sort of charge transfer resistance within the lithium, or sorry, within the silicon itself as it's being lithiated. And so this is showing us some amount of detail as to what might be going on, but it doesn't give us the explanation for why this is happening. And so, our group is still working on the exact explanation for these things, but here you have just more information about what makes the Si30 so great. Here you have some SEM micrographs of the different electrodes um, under different lithiation states. So basically, well, they're all nominally in the same lithiation state, which is delithiated. Okay, but we've taken images of our electrodes before lithiation, images of our electrodes after 20 lithiation delithiation cycles, and then images of the electrodes after 50 cycles. So on the left you have pure micron particles. On the right you have pure nano, and in the middle this Si30 composition. So here you start to see some information about like what changes the electrode undergoes during lithiation. You see that those very crisp crystalline particles of silicon in like prior to lithiation get really well, they coarsen and they change a lot in morphology after lithiation delithiation, especially in the case of these micron particles. There's been severe volume changes and all sorts of things causing them to lose their original structure. Um, the nanophase to eye looks actually pretty good. It sort of it maintains to some extent its original fine particulate structure after lithiation and delithiation, and that would normally seem to be a good thing. That would, on the right, you might say that that's what you expect and hope your a good quality electrode would look like. Okay, but the problem is that what's happening here on the right is constant formation and reformation of this interphase layer in between the silicon and the electrolyte, and that's just causing massive amounts of resistance to build up in the cell, even though the particle size is staying quite small. And so you kind of want, to some extent, the properties of a large particle, but you want that particle to stay in contact. And so I think what we're seeing here in the middle is that large particles of micron-sized silicon are being held together by small particles of nano-sized silicon. And even though those large particles are sort of coarsening and amorphizing over lithiation and delithiation, they're staying in contact because of the kind of nano phase particles that are stuck and kind of acting as almost a binder in between the large particles in the middle. So I'm just going to show you some performance and some different tests we ran afterwards. So most of this is kind of more on the applied side, trying to figure out how to make these electrodes even more higher performance, and basically just testing different. Well, first of all, putting these electrodes in the presence of a full cell. So now we're cycling them against lithium iron phosphate once again, um, and changing the relative ratios of the anode to the cathode. So if you change the amount of potential cathode lithiation supply in the material, that changes P, and if you change the relative amount of anode, that changes the amount of N. That ratio will give you a kind of some expected balance of the cell. It's very difficult to actually define this ratio, and so I'm going to show you at least here one slide on why this is such a weird metric to calculate for silicon. The problem is, if your silicon capacity is fading so much on each cycle, you're actually changing, the relative um, capacity for silicon on the anode side as compared to the cathode side in each cycle. And so, how can you define a single metric that relates to the cell balance? It's basically not possible with the material that's not very stable. And so, what we do in our group is we have to define metrics based on kind of theoretical capacities of silicon versus whatever counter electrode we're using. We have in some cases, we define our NP ratio based on a very optimistic capacity of silicon, 2300 milliamp hours per gram. Sometimes we use a much more realistic value of about 1500 milliamp hours per gram. This gives us numbers that are kind of in the realm of realistic and what ends up actually happening in the cell. And so anyway, you can kind of use either one. It doesn't really matter which metric you use, as long as you kind of explain how you're defining it. And what we see is that as we thicken up as the loading on the anode side increases, that means the NP ratio goes up. The discharge capacity of that electrode goes down. And so as we thicken up our electrodes, this is common among any kind of active anode or cathode material, but the severity of this is pretty marked. So it's important to note that our cells are only really working well when they're very thin. Here we have the same data shown in aerial capacity. So this is on a per square centimeter basis. And you can see that maybe there's a possible case to be made for a kind of a maximum in the aerial capacity as you go to just the right thickness. But at the end of the day, it's all pretty close, and the anodes don't perform a lot differently depending on aerial capacity as you load them up. Our data, compare favorably with other data in the literature. Depends on obviously always where you look, but as far as pure silicon anodes go in the presence of a liquid electrolyte, these are some of the highest capacities over the first 100 cycles that we've ever seen. And so we're pretty proud of the performance we're able to get out of these particle size mixed electrodes. All right, I have a few more minutes, so I'm going to talk about a second strategy, which is doping. Okay, this is not that um, surprising of a strategy, because I mean, I'm sure you're aware that there have been 50 or more years now working on silicon as a really important material for transistors and for all of computers. And so people have learned a lot about doping and its effects on silicon's both conductivity and other properties like lattice expansion, lattice contraction, and so on and so forth. Um, so we decided to try and see what would happen when we dope silicon with a substitutional dopant. What would that change in terms of the lithiation delithiation properties of that material? We chose phosphorus as our first dopant of interest because it has a massive solubility in silicon. You can actually get a 3 atomic percent phosphorus into silicon at equilibrium. And so for that reason, we're going to look at the phosphorus results here first today. So on the left, you see, now these are non-optimized cells, so they are fading pretty fast in terms of capacity, but we're seeing capacity as a function of cycle number depending on the concentration of phosphorus in the lattice. So as we go from low phosphorus loading to high, and we compare that to the control, okay, if your control has 0% phosphorus, initial concentrations of phosphorus up to maybe 0.05 weight percent, 0.1, 0.2, and then even at just one, sorry, these are atomic percent numbers, you already make massive disruptions to your silicon lattice to actually make it as completely ineffective as a lithiation uh, anode material. So this is an interesting set of data that we published 2 years ago now. But this was our first kind of foray into doping, and so I'm going to use this as a good textbook example of how doping can really dramatically change the outcome of results for lithiation. We tried different methods for getting the phosphorus in. So we would use, for example, um, different heat treatment temperatures. So we have a high and a low here. This high number turns out to be about 1100 degrees Celsius. The low is about 800 degrees. And so different temperatures, different soaking times in the presence of phosphorus give rise to, of course, different phosphorus distributions in the material. And what we always found was that if you soak for a very short amount of time at a low temperature, um, you so in other words, preferring to put the phosphorus at the edges of the particles as opposed to homogeneously throughout the particles, you always had a better outcome. And so it was all about surface doping. You want to get phosphorus as close to the surface of the particles as possible in order to make the best effect. And you want to have a relatively low concentration of phosphorus. Here are some of the best data that we've ever collected. So this is kind of our performance metric today. Um, what we see, the heterogeneous distribution of phosphorus in the lattice, what we call this hetero material right here, in an Si30 format with phosphorus doping, we can achieve values of around 2,000 milliamp hours per gram for around 150 cycles. That represents about 80% of the original capacity after around 150 cycles. So you know that is what it is. That doesn't sound like a lot of cycles, and but that capacity is relatively high, and it depends on what you want to get out of your battery anode. Obviously, here, if silicon is of interest to you, you'd probably um, have an application where you didn't expect to cycle it more than a few hundred times in its lifetime. So that's just something to think about. Um, and yeah, very those are among the highest results that we've ever seen reported in the literature for a liquid electrolyte pure silicon electrode. So how does that compare to Jeff Dahn's 4 million mile battery? Okay, if you put graphite into a cell and you kind of choose a typical cathode and make a sort of state of the art battery today for an electric vehicle, you can get 400 miles per charge with a good quality lithium-ion battery based on graphite. Now, Jeff Dahn has shown that that battery can last for a total of 4 million miles. I'm sorry to use miles here today, but those are the units Jeff picked for his research. So, of course, that's over 600 kilometers per charge. It's honestly not that bad, and that's already a really really good battery right there. Very reliable and a decent amount of charge per cycle or per per charge discharge cycle. Okay, so what does that? How does that compare to our pure silicon case? Our pure silicon batteries can probably get around 120,000 miles total in their lifetime. Okay, so not 4 million, 120,000 this time. But each charge gets you 800 miles. So you have double the basically the capacity or the energy density as you can get with graphite over, and that's an average over this lifetime of 120,000. Um, there are many, many other people who are looking into just, serendipitous or I should say synergistic combinations of silicon and carbon. So don't go full silicon, but just put a little bit of silicon in there. And what can you do with that? Our group has also been getting into that. And here's just a representative case of a really nice silicon carbon composite material. That one gets maybe 600 miles per charge, so something right in the middle of 400 and 800, and can last about 200,000 miles. So this cell, has a different set of trade-offs. But at the end of the day, these data show us that even though silicon, sort of on paper, looks like a really, really an easy material to beat graphite with, it's really still to this day extremely difficult to beat graphite. Um, as I have a few more minutes, I'm going to talk about just some. I'm going to show you these crystal structures of sort of how silicon evolves as it gets lithiated all the way up to Li15Si4 to give you an idea of when and where those bonds get broken in the silicon structure. So it undergoes this sort of, I guess, 1, 2, 3 step process at least in most silicon anodes. And you can see that even after step 1, the formation of the phase LISI, okay, we've only got 3 of the 4 bonds remaining that were in the original diamond structure of silicon. Okay, in step 2, we now only have 1 to 3 out of the 4 original bonds remaining in each silicon site. And so that depends on which silicon you are, of course, but all bonds are broken by the time you get to Li15Si4. So future work in our group is going to be to try to harness just this initial reaction here to try to stop it before we start cutting and breaking all of the silicon bonds in the material. We think that this reaction should be much easier to reverse reliably over millions of cycles, like Jeff Dahn's graphite cell. Okay, but stopping it here is very difficult. Other future work in our group, we're looking at higher charge and discharge rates. So silicon, it turns out, is a very, very fast material compared to graphite, and that's on its side as well. So you can actually do rapid charging with silicon at extremely fast rates, and our group is looking into that. This slide is actually not the best representation of that. We're now looking at even higher rates of like 6 amps per gram, which is on the order of about 20-minute charge time. Uh, Very, very fast charge times. Graphite doesn't love to be charged that fast, and so graphite takes a little bit longer. Other things are working on in our group are different ways of synthesizing silicon, and here you see a new plasma enhanced coater that we've recently been starting to commission. And so, yeah, making silicon in a roll-to-roll process directly from a plasma, where you just take silane and you deposit silane directly onto copper foil. This has the potential to revolutionize things, because here you don't make particles and then mix your particles together and put them together at an electrode. You just make your electrode in one direct step directly onto copper foil. Um, and so, yeah, this is research that's ongoing in our group. So with that, I thank you very much for your time. These are the people that do all of this work. And if you want to find out more information about our group, you can look us up here at www.montana.edu/Stadie group. And yeah, again, my name is Nick Stadie, and you can also feel free to email me with any questions. So thank you very much.
All right. I'm not sure if you can still hear me out.
Yep, I can hear you.
Because my screen froze. I think
Okay.
the second you start talking, but I'm here all the time.
Okay, great. Well, I couldn't see anything the whole time anyways, so unfortunately I can't see the audience or you right now. So
Right. So the now is the time for question and answer. If the audience have any questions, you can type in this chat box. And if you want to speak, ask me in the chat box so that I can put you on the stage. I think this like software has a weird way to, have
yeah, no
um,
problem.
audience participating in
Hmm.
discussion and things. All right. So while we are waiting for questions, I have a few questions. So you like when you test the mixture of the silicon, like the nanoparticle and the micrometer particle,
Hmm.
um, you I think you speculate that the um, particles goes into like the interstitial sites
Yeah.
and like fill that void there. Um, but you didn't manage to like take the measurements or like have any evidence on that, right?
No.
You just did. So, yeah.
Yeah.
So I was wondering if there are any easy way to do so,
Hmm.
or what's the problem? Why you cannot? Uh, yeah.
Yeah. Well, um, it's very difficult to do this kind of. I mean, so maybe if we had some more advanced imaging facilities in terms of electron microscopy, one could get at these answers. Um, it would be nice if we also could build our electrode and then simply make a cut, so that we could see a cross section of it. This would be a nice method as well. So I think having tools for cutting through and cross secting the electrode and then also imaging it, you know, there are a lot of facilities that can do this. So maybe we just need to find the right collaborator, but we don't have that here at MSU. So we haven't been doing that in our group.
I see.
It's a good point though, and it encourages me to really do that. I should.
Right. Oh, I was even thinking about like um the pure crystal should have the size of the interstitial site reported, I guess, and then
Mm,
you can simply see whether the size of the nanoparticle fits into that. But
yeah,
maybe that's
there might be.
oversimplified.
Yeah, maybe like some mercury intrusion experiments where we actually try to figure out what the void space looks like in these electrodes. That could be handy. Or maybe even with another method that you could, where you have some kind of a dye, or I use that word very loosely here, but like if you had neutrons, you could put maybe water in between and try to look for where you see contrast, and maybe make a tomograph or a tomographical image somehow of the porosity network inside of the electrode. I'm sure that there are facilities that do this. We definitely don't have easy access to that, and so that's a little bit why we've mainly been approaching this just from the question of what's the outcome, rather than trying to learn as much as we possibly can about what's going on. Um, the funding that we have is highly applied, so um, really the Army is just interested in how well do these things work, not how do they work.
Okay. All right. Still waiting for questions from the audience, but in the meantime, I have another question. So, like, toward the end of the presentation, you mentioned that like the way um, you want to stop the bond breaking at like 3 or 4 bonds,
Yes.
right? But you also mentioned that it's hard to do so. I'm wondering why, because isn't it just like the correct ratio between lithium and silicon?
Yeah, great question. So you would think so, but the problem is you don't really control. I don't show any images here um, of what the voltage profiles look like. Maybe I can try to see if I have some in the extra slides. Don't see any. Okay, so without wasting too much time, I mean, I don't show you the nice data, which are you would want to see the voltage profile here. If you could see the voltage, the shape of the voltage profile, then you could say, okay, why don't you just go to the right stoichiometry along the x-axis, and you can use even voltage to to stop the reaction right there. The problem is if you dose the material with a certain amount of lithium, you cannot prevent that part of the material goes all the way to Li15Si4, and meanwhile the
Um,
other part stays at pure silicon. So you
oh,
can
right.
only,
Like you mean like
right? Yeah,
inhomogeneity?
yeah. And those
Mm,
voltage steps are so close together for these different reactions that you can't really
mm,
easily control by setting the
mm.
potential to restrict the reaction further from that one. And so yeah, basically keeping it from going from here to here is very difficult. There's an over potential associated with these reactions as well. So if you already basically go past this potential, even just in reality, when you're trying to just get this reaction started, you have to kind of go past this potential even just to get this one to get going. And so yeah, it's a problem.
All right. So I got a question from an audience sent to me privately, I think. Um, oh, first he said that it's very good talk, but I'm wondering whether the silicon anode he mentioned is pure or they mixed with graphite.
Hmm.
Also, what is the active material loading they typically taste? And it is, and is it LFP cathode?
Yeah. So all the data I showed here are for LFP cathodes. So the answer to the last question is yes. Um, the loadings that I'm showing you, I can maybe show you here. So this is the loading reported in, oh no, sorry, that's the current rate. Um, so let's see. I thought I had the loadings, but I guess I don't show the loadings here. Okay, but this is the NP ratio. Um, yeah, this is a good question. I thought, oh, maybe I did earlier on in the talk. I know I saw some numbers. Okay, so here you see some loadings in milligrams per square centimeter. So our typical loadings are around 0.75 milligrams per square centimeter. These anodes are the ones we kind of produce every day, and um, they are the ones that you will see most commonly in other slides on this talk. So that loading is not very high from a commercial perspective. You would want that loading to get significantly higher. to be able to commercialize these cells. But we're kind of working at the coin cell and small pouch cell scale, and so we don't bother with doing a ton of work on trying to make these thicker and make them also perform well as a thicker anode. All of the anodes that I showed you, except for in one slide, were pure silicon. So this is a good example here. This red material, this is what we call Si30. It's 30% nano, 70% micron. This is a pure silicon electrode, no carbon. It's got some binder inside. We use a cellulose type binder, so it's an aqueous dispersion, but there's no carbon content in these materials at all. Whereas on the one slide where I showed the carbon silicon composite, we have here, okay, a comparison between our best pure silicon anode and one sort of pretty representative but standard. I mean, again, you can kind of tune these very, very up and down depending on how much carbon and silicon you put in. So the ratio between carbon and silicon changes the outcome a lot. But this is just one example of a carbon silicon anode that we made in our group using a traditional CVD reaction of silane onto a carbon scaffold. And you see that you get pretty good reliability. This is nowhere near as good as graphite, but it is some decent stability. It reaches 80% of its original capacity after 300 cycles. So this is a silicon carbon composite with about 50-50 silicon to carbon.
All
Hope
right.
that answers some of your questions. But yeah, our group is
Yeah.
tasked specifically by the Army to try to figure out how to make a 100% silicon anode if a viable option to replace graphite. And my answer to them is you can't replace graphite. It's very, very difficult to beat that material. And silicon can have certain advantages. Like here's a trade-off. If you want to have a cell that with a double the energy density of a standard lithium-ion cell, this energy density here includes all of the weight of all the other components, like the cathode, the cell casing, the electrolyte, everything else. You can see that even with 10 times the capacity, you still don't get 10 times the energy density. You get about twice the energy density or double. But you pay a very heavy price for that because your cell now cannot last for 4 million miles. It can only last for 120,000 miles. So much reduced battery life, but each charge discharge cycle is significantly longer lasting.
All right. Yep. Another question. I think this is sent publicly. Do you see the question there? Could you share your perspective on solid state electrolytes
Mm,
with silicon anode or lithium metal anode?
yeah. Solid electrolytes are again another. They're an open question as to whether there's really a true benefit to be gained, or whether it's just a trade-off again, just like everything else. And I don't know enough about the solid state batteries to say for sure. I know that there are friends of mine and even chat a good friend of ours, Wolf Zayer over in Germany, works on solid state batteries and claims that they will replace our liquid electrolyte batteries here in the next 10
Mm.
years. But all solid batteries have the main problem that they of interfaces, and interfaces are very problematic. They crack, they change, and it's a lot more difficult to heal an interface when it's between two solids than it is when it's between a liquid and a solid. And so all the data I've seen for silicon in solid electrolyte batteries, they look okay, but you must note the caveats, which are a lot of pressure has to be kept on the cell during its operation, um, and that's a main disadvantage. It also costs a lot in weight to build your cells that way, and so yeah, I'm not convinced that it necessarily will work. But you should invite Wolf to talk here about solid state batteries.
That's true. That's true. Yeah. He will say otherwise.
Yes.
All right. Is there any other questions from the audience? So I think today, at peak point, we had almost 30 attendees.
Great.
All right. Last chance for the audience to ask questions. Because it's like almost almost I think it's midnight over
Yeah.
there already. So um, but yeah, like Professor Stady said, if you have any other questions, you can send him emails.
Yes.
Yep.
I will show.
Uh,
Yeah, this slide again.
there.
So yeah, please contact me if you're interested in our work or coming here to do a postdoc or grad school, depending on your level.
Are you still open for like postdocs and
Yes.
graduate positions?
Yep.
All right. Good opportunity to travel to the US,
Hmm.
and especially if you love being in the wilderness.
True.
All right. So I think I don't want to take more of your time, especially at this time at night. So thank you again, Nick, for giving the talk today.
No problem. Thanks for having me.
All right. I will talk to you soon. All right.
Sounds great. Talk to you soon, chat.
Yep. Goodbye.
Bye.